every calculation we do in engineering has assumptions made. And this is reasonable for many engineering calculations, just using a 9.81 value. All right? What happens if you start talking about high altitude kind of problems? What if you went up to an altitude that was, say, half the radius of the Earth? Pretty high up, okay? You're going to expect to see these two masses, the object and the Earth's mass center, being significantly greater than the radius of the Earth. So what we do in that case is we have to have an allowable adjustment for those kind of calculations. And just real briefly, let me just run through a couple things with you here, show you that. We know from this relationship that we played with right there that the gravitational constant, G, capital G, times the mass of the Earth is equal to AR squared. Or, let me just write it. Let's see, how did I do this here in my notes? I called it G naught, which I labeled right here, times R squared. And then, let's say we are now, here's the Earth's surface, here's the radius of the Earth, and let's say we're now up here at some height h. Here's our mass up here. Right? There's a force of attraction that exists here between the mass and the mass of the Earth at some distance separating them of r plus h. So if we write that equation, then we have that the force is equal to the mass of our object times the gravitational acceleration at some height h. And this is going to be the force of attraction at this height h. Let me label it that way. And that has to be equal to the gravitational constant times the mass of the object times the mass of the Earth divided by r plus h squared. If we come in there now and replace GME with this G naught value, and we lose the mass of the object here, we have that numerator being replaced with G naught R squared, G times ME, divided by R plus H, the quantity squared. We get the gravitational acceleration that exists at some height h. And this is shown in your book. Like that. Everybody see that in the textbook? If you don't have the text yet, it's right there in chapter 1. Okay. You're going to notice as you read and study engineering or science textbooks, math textbooks, they'll say obviously, or it can be shown that, and then they show you something. They write something down. But they don't, oftentimes there might be a whole page of calculations to explain that obviously, or it can be shown that kind of a thing. So this is one such case. They just sort of state this without the explanation of where it came from. So at some altitude h, this would be a formula you're going to use. And what value of G naught are you going to use then here? 9.825 for the non-rotating Earth. Good. Okay. Now, let's go ahead and get going on rectilinear motion. And then we'll try to be done by about 20 after 5 today. Okay? Got a little over a half an hour left. Any questions on this stuff so far?
Yeah, if you're still being if you are dealing with something off the surface of the Earth by enough height to warrant using that formula, wouldn't you still be subject to the, well, in many, okay, that'd be by application, because you could still be subject to the centrifugal force of going up.
Not if you're outside the atmosphere, which is where most of the satellites in the space shuttle operate.
Okay.
Okay. Now, you know what altitude the space shuttle usually operates at?
Like 200, 300 miles?
Yeah, typically. Okay. And very low orbit satellites are up over 150 miles or so. Typically, they're higher. How long does it take for a satellite in normal altitude orbits to go around the Earth?
About 90 minutes.
About 90 minutes. When I was a kid, the first Sputnik and early U.S. satellites were being put up, and we all knew that. Most people nowadays don't realize that at all. They're clueless about it, about how long it takes an object to orbit the Earth, a satellite. How high are the geosynchronous satellites, roughly? Which means that as the Earth rotates, that satellite always stays in that fixed position in the sky, your DirecTV antenna or dish, that kind of thing. How high are those, approximately?
30,000 kilometers?
Which is around 20-something thousand miles.
Yeah.
20-something thousand miles. Okay? We'll explain why that altitude is so critical. And that altitude is actually starting to be heavily populated with lots of stuff because of that valuable space. We can't call it airspace, can we? Okay, because there's no atmosphere up there except for occasional molecule. How far is the moon from the Earth?
250,000 miles?
Roughly 250,000 miles. And there was an asteroid that passed between the Earth and the moon not that long ago, a few weeks ago, that was only around 44,000 miles from the Earth. A pretty good sized asteroid, about the size of a 10-foot building. If that had hit the Earth, it would have created a sensation. Significant. So those kind of little bits and pieces of knowledge you can read in the newspapers or magazines and that kind of thing, and as you go through engineering school, you'll become more and more exposed to that kind of stuff. So just keep your ears open. I mean, this is just one area of science that might interest you. Okay, let's go ahead and get going on what's called rectilinear motion. The way the textbooks present this topic is treating an object as if it's traveling in a straight line. And I'm going to set this up similar to what we see in our textbook. And then I'll explain a variation on it that you'll find useful throughout the course. If we call displacement along this straight line S, measured from some reference point, this is starting point 0, and we have an object out here at some point P, and then the object moves to some point P prime. You can see that this position of point P happens to be at some position S on the path. And then if the object has then moved from P to P prime, it has traveled some change in S. Now we know that the object traveling that change in position divided by that change in time that's occurred, that's taken to go from P to P prime, is going to be equal to the average speed or the average velocity. And And what you've learned in first term calculus, matter of fact, probably about the second week of first term calculus, is if you take the limit of this, as you let this time shrink towards 0, you get ds dt, which we call the instantaneous rate of change of displacement with respect to time, which is a mouthful. So we abbreviate that and call it the instantaneous velocity. Right? So where is the object? Where is the object when it reaches or has this instantaneous velocity? V, we'll call it. Where is the object here? If it's here at P, at distance S, this is the change in time that we've been, change in position that we've been using, and it took a finite amount of time to move from here to here. Then as we let this change in time shrink to 0, we're really talking about the speed the object has right at this location, isn't it? It's the instantaneous speed it has to have, or happens to have right here. So right here is where this velocity value is. Now we know that if an object has a certain speed at a certain location and it goes through some displacement from that location, its speed could change, couldn't it? But for that speed to change, what would have to occur?
Change in acceleration.
There has to be a change in the velocity to occur, which is called then the acceleration, isn't there? Isn't it? Okay. So we have to have then, if we're interested in the object, what it's doing here as far as its speed goes, and then we're interested in what its speed might be after it's transitioned some displacement, then we have to then look at the derivative of this instantaneous speed, don't we? Okay. So if the object is carrying some speed here, and it moves over here, and it now, at this point, is moving at some speed v plus some delta v, right? There's been something that's happened to allow for it to have this new velocity over here. Okay. So what we'll do is we'll now look at the change that's occurred in the velocity during that motion from P to P prime. And there's, again, that same amount of transition in time that's occurred. And this is going to be called what? Finite change in velocity over finite change in time. Average acceleration. Average acceleration. If we then apply the limit to this, we get the derivative of that speed with respect to time, which is the instantaneous rate of change of velocity with respect to time, which we want to shorthand our vocabulary on, and we call that the instantaneous acceleration. Just abbreviated A. Instantaneous acceleration. Where is this occurring? Over here on the path. Again, at position P. At position P. because we've allowed the time change to shrink in the limit towards 0. So the object is carrying, it's at physical position S on the path. At this position S, noted as point P, it's carrying an instantaneous velocity v, and at that same location, it's carrying some acceleration. If that acceleration remains 0, and it's carrying some velocity p when it passes, some velocity v as it passes through point P, then what's it going to have when it gets over here to P prime, if that acceleration was 0?
Same velocity.
Same velocity, no change in velocity. Okay. That's like you cruising down the road, applying the same amount of energy on your bicycle, your motorcycle, or your car, the exact same amount of energy on a level straight path, and you're going to maintain that constant velocity then. If you put the brakes on, you know you're going to slow down, okay, right? Or all of a sudden the wind picks up, blowing against you, you're going to slow down, but you're applying an acceleration in a direction opposing your motion, and that causes you to decelerate or slow down. Okay. Now, what they do not mention in the book is that this mathematics right here, which essentially are two differential equations, this one, ds dt equals v, and this one, that acceleration equals dv dt, these are first order ordinary differential equations. And some of you are taking differential equations this term or last year, and you've actually solved this kind of stuff back in second term calculus, these kind of problems. What the book does not tell you when this discussion about rectilinear motion is this stuff, these equations are perfectly valid for curved path motion with one limiting criteria. So here's the path. If you use what's called the arc length parameter, which some of you saw a glimpse of in calculus, then that means you're simply looking at distance along the arc or motion along the arc. It's just like you've seen horses on a wagon where they have the blinders on. They do that for a reason, so they don't get distracted and go off some other direction because they see something that interests them, or they don't shy away from something that's off to the side. So if you think of yourself having blinders on and only looking right in front of you as you move along the path, and only interested in that instantaneous speed along the path and the instantaneous acceleration along the path, these equations are perfectly valid. In calculus, you have seen that when you're on a curve, isn't there more than one acceleration? And mathematically, and we'll go through the derivation of all that later in this course. But what we're seeing when you're on a curve is what these equations are describing here is this A is the tangential acceleration. There is another acceleration that exists if you're on a curve. Something that has to force you on that curve. And we'll study that, as I said, a little later. And that's going to be perpendicular to your motion. And we call that the normal acceleration, normal to the curve. And that's what is actually going to pull you through the curve. You wouldn't go on a curve otherwise. You wouldn't follow a curved path if there wasn't something pulling you to want you to go that way. And then in first and second term calculus, you learn things about curvatures, concave down, concave up, and the transition between those is a point of inflection. And right at that spot is where you lose a normal acceleration. And then once you change the concavity of the path, you're going to have to then, and you go into a curve like this, over in here, you can still have a tangential component of acceleration, like hitting the accelerator or slamming on the brakes or wind resistance. Or if you ski or snowboard, hitting that soft snow after you've been on an icy surface. Okay? That's a tangential thing. And if you're on the curve, then that normal acceleration to then pull you through the curve the other direction is going to have to pull you or point towards the center of curvature. Okay, again, this is all kinematics. This is geometry of motion, talking about the velocity and the acceleration. Everybody still awake? Any questions so far? These problems in the early part of Chapter 2, I want you to start your problems here and try not to grab some formula that might be several steps later. And I'll explain that in a couple of minutes. No questions so far?